Hello there, welcome to today's webinar, From Aerospace to Autonomous Systems, Tactical Grade IMU for Demanding Applications, sponsored by Inside GNSS, Inside Unmanned Systems, and SBG Systems. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders who will describe the Pulse-40 new miniature MEMS-based Tactical Grade Inertial Measurement Unit designed and developed by SBG Systems for demanding applications spanning aerospace to autonomous systems. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Expert panel session with all three of our panelists. Now, we've invited you, along with over 200 professionals from 42 countries representing a variety of industries, and over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar to be of value. Now, before we get started, Richard Fisher, publisher Inside GNSS and Inside Unmanned Systems, would like to take just a moment to welcome you and introduce our main moderator for today's session. Richard?
Lori, thank you. So on behalf of Inside GNSS, Inside Unmanned Systems, and our sponsor SBG, I extend a warm welcome to our audience from around the world for today's webinar. We are delighted you're here today to learn more about this exciting launch, and we appreciate SBG launching their Pulse-40 with the Inside GNSS and Inside Unmanned Systems media brands. Now I'd like to introduce our moderator for today, Alan Cameron. Alan, the floor is yours.
Thank you, Richard. Thank you, Lori, and welcome to everyone around the world. We have an exciting webinar in store for you, and we'll go deep into technical details of inertial technology. You have a brief glance here at our panelists from SBG Systems, and we're going to hear from the Chief Technology Officer, the Business Development Officer, and the Test and Qualifications Engineer. I will introduce each one of them in turn when it's time to speak. But right now, Lori, let's have a bit of speaking from the audience.
Absolutely, and coming up on your screen is going to be our very first poll of the day. We would like to hear from each of you. What IMU application or applications are you working on? And in this case, we are asking you to select all that apply: navigation, integration with GNSS, antenna, camera stabilization, mapping, survey, robotics, aerospace defense. So it looks like we are coming in with 71% navigation, integration with GNSS, 24% antenna, camera stabilization, 44% coming in with mapping, survey, 29% robotics, and 34% aerospace defense. So, Alan, any thoughts here?
Well, other than telling the audience that all of you are in the right place to learn more about your applications, I'm going to defer to one of our panelists. And members of the audience, you have not been formally introduced to Alexis Guinamard, but we're going to hear from him briefly. Then I will introduce him. Alexis, do you have any comments on the distribution of the applications that you're seeing here? Does this reflect your client base or the general industry? What can you tell us?
I would say that in an interesting split of the applications. What I see is that all the navigation applications and mapping survey application require a very high precision IMU to operate properly. And so that's a very, very nice insight. More generally, these applications are very common to SBG systems. We will see right after how the Pulse-40 can answer to these markets. But yeah, that's a very interesting insight.
Thank you for that preview, Alexis. All right, audience, now is your turn to meet Alexis properly. He is the Chief Technology Officer and co-founder of SBG Systems, a supplier of miniature high-performance inertial navigation systems. He holds a Master's of Science degree in Embedded Systems from École Centrale d'Électronique And for the past decade, he has led the development of cutting-edge navigation algorithms and hardware, including attitude and heading reference systems, inertial measurement units, inertial navigation systems with embedded GPS, and more at SBG Systems. Alexis, please tell us about the Pulse-40.
Thank you, Alan. I'm really excited to present this new Pulse-40 into this webinar. I'm going to start my talk by presenting our company for those who are not so familiar with SBG, and then also I will present our expertise in the inertial systems, and then of course I will go into the Pulse-40 presentation and give a brief overview of the manufacturing process. But the manufacturing process will be much more detailed by the next speaker, Emmerich. But before starting, I wanted to highlight some common mistakes that are made when considering MEMS IMU design. So the first mistake is that many people think that you can just buy a 3x3 millimeter sensor chip that is really widely available on the market now, and then you will make an IMU out of that. It's important to know that the vast majority of the MEMS IMU are now produced and designed for consumer applications. So they usually have some nice characteristics. For instance, they have a low noise. They are excellent sensors for gesture analysis, for simple camera stabilization, but it doesn't make an IMU. If you want to have a high precision, if you want to address high precision application, you will need to integrate a lot more intelligence aside from this sensor chip. You will need to address the very high sensor-to-sensor performance discrepancy. So one sensor combo doesn't behave exactly like another one. All these designs do not consider the long-term stability. They have no sensor calibration at all embedded. They have no mechanical integration. Much care needs to be done on that aspect. And no advanced signal processing are embedded into these sensor combos. The other common mistake is just looking at the Allen variance, angular random walk, and bias instability, and then consider this is the only factor that you need to check when comparing to IMUs. Here it's an example of a sensor that you may find on the market actually, which provides an excellent bias instability. The curve is going down very, very well. But if you look at the right side of the curve, then you will see that it goes up dramatically right after. And so only after 100 seconds of integration, you already increase the noise, and so you won't get much performance out of this sensor. So I wanted to remind that Allen variance is the next excellent tool for sensor performance measurement, but it's not the only parameter to look at. The random walk, the rate random walk, which is the rate of increase of this Allen variance curve, it's also an important factor. And other parameters like startup bias, long-term stability, vibration rectification errors need to be considered if you want to know how your IMU will behave in the real world. But yeah, let me give you some introduction about SBG Systems. So we are a leading supplier of orientation, stabilization, and navigation solutions. We are headquartered in France, and we have an international presence, more than 800 customers over the world, and more than 25,000 inertial sensors on the field. And if we go back to the history of SBG back in 2007, when we started the company, at the very beginning of our history, we knew that it was a key to invest a lot of efforts in calibration of inertial sensors. So the very first inertial systems that we delivered were already calibrated in a fully automated and industrial motion simulator with temperature compensation. Over the years, we introduced various improvements in our tools. This allowed us to release high-performance inertial navigation systems, the Equinox, Ellipse, Apogee, and then in 2017 and the years after, we introduced our new facility with the 2-axis rotary tables with temperature chambers. This allowed us to implement a 100% automated calibration process with no human intervention during the whole calibration process. This is really important to understand that, because initially we were developing mainly inertial navigation systems, but we always had IMUs inside our products. So that becomes quite natural for us to release on the market an IMU to take all the benefits of our expertise in the inertial sensors, calibration and sampling and integration. So what are the fields of expertise you need if you want to make a good IMU? The first aspect, which is really important, is the MEMS sensor itself. Of course, it's really important. So at SBG, we don't develop the MEMS elements, but we have selected partners which we qualified using a very, very deep qualification process. So we know exactly how the sensor behaves. We have also an expertise in mechatronics, electronics design. Of course, this is a key to develop a miniature IMU. Also, an expertise in signal processing. That's also a key to ensure that you have a proper behavior in all conditions, especially in vibrating environments. Calibration algorithms expertise is also mandatory if you want to make sure that the system will behave perfectly fine in all the temperature conditions, all the dynamics. And something that makes SBG somewhat different from other IMU manufacturers is that we also have some expertise in inertial navigation. Since we developed INS systems for more than 15 years, we know exactly what we need in terms of IMU performance parameters. We are also an end user of this IMU. So we need the best IMU, and we want it with the Pulse-40 to get the best IMU possible. And yeah, that's probably something really important to see SBG as a leading supplier of IMUs. Now, why did we design a new tactical grade IMU? What was our main requirements? So we wanted to develop a new IMU, of course, for high performance markets. This was really our initial focus. We wanted to have something really compact, really robust, and really capable of operating in really constrained applications. Of course, we wanted to leverage on our expertise in inertial sensors. And finally, we wanted to have a sensor that would be easy to integrate, something that you could, for instance, just plug on a PCB with a board-to-board interface would be really, really fine for that purpose. So let me present you the Pulse-40. So the Pulse-40 is a 6 degrees of freedom IMU composed of a redundant set of 3-axis gyroscopes, accelerometers. We also embed a temperature sensor to allow the thermal calibration, of course. We have an internal clock that runs the sampling internally at so that there is a high frequency sampling on the gyros accelerometers at more than 4 kilohertz for accelerometers and 6 kilohertz for gyros, and the main loop runs at 2 kilohertz for all the calibration process. A continuous built-in test ensures that we deliver data that is verified at some point, so we are pretty sure that we deliver valid IMU information, and we can warn the user if there is any problem on the IMU measurements. The system can be synchronized. We will talk about this later on. We have a single UART interface, a very simple interfacing scheme. So as I mentioned, initially we wanted to have something easy to interface, something also very small. So we developed an IMU with an optimal swap, also optimal cost. We will see that. The direct PCB mounting makes it really straightforward to integrate this IMU into the customer application. 30 by 28 by 13 millimeters size, less than 12 grams. That's a very small device, for sure. And as I mentioned, we have a UART TTL interface. The mechanical and environmental specifications are also very interesting. So the sensor is qualified from -40 to +85 degrees Celsius. It's important to know that this spec applies for the storage, the operating conditions, but also the fully qualified condition. Sometimes the calibration range is quite limited, but here we have the full performance that is guaranteed over this full temperature range. We can handle 10 Gs of vibrations, operate under strong shocks, and we have also a survivability of 1,500 Gs. As you can see on the pictures on the right, many tests have been done in shakers, in temperature chambers, and so on, to ensure that the system is behaving exactly how we want. Emmerich is going to talk much more about that. Regarding the performance, we have a cutting-edge MEMS design that enables an excellent noise and bias instability, and a ultra-low vibration rectification error, which allows this IMU to operate in very harsh conditions. So the gyro can operate up to 490 degrees per second, and the accelerometer up to 40 G. It's important to know that this system has no export restrictions, but we still have a higher range on the gyro option with 2,000 degrees per second, but this unit is export controlled. So the in-run bias instability of 0.8 degree per hour on the gyro, which enables a tactical grade level, and 6 micro G for the accelerometer. And another important parameter is the high bandwidth and the low latency of the sensor, which allows operation in highly dynamic environments. Also optimal performance if you have high dynamic motion acceleration coupled with rotations, then you can maintain a proper performance. That's really important. And as I mentioned, the VRE very low, 0.2 degree per G square, degree per hour per G square on the gyro, and 30 micro G per G squared on the accelerometer. Some figures now. You can see here the gyroscope Allen variants that we've made on more than 30 gyros, I think. You can see that the sensors are really repeatable, really consistent to each other. And we see that the bottom of the Allen variance is reached around 200 or 300 seconds. And it doesn't go up very fast right after. So that's really, that means that the bias of the gyro will remain quite stable over long periods of integration, which is really important, especially when you consider INS applications or mapping applications. This will enable low heading drift, for instance. Same figure for the accelerometer. Once again, the stability is really good and doesn't go up on the right. So that's very interesting to enable long-term navigation applications. Then we show the temperature sweep tests. You can see that the gyro remains really stable or when exposed to temperature variations, with a variation of around 50 degrees per hour or something. So very constrained variations of the gyro bias. And for the accelerometer, we have pretty much the same behavior with very stable performance over the full temperature range, less than 200 micro G variation. So very interesting. I wanted also to highlight the clock modes of this IMU. We designed the Pulse-40 to be as easy as easy as possible to integrate. So both on the hardware side to plug in on a PCB, but also on the software side. So the clock synchronization has been designed. So you have different modes. Either you can run with the internal clock of the IMU. So in that case, the internal clock generates a 2 kilohertz sampling and signal processing main loop. And then you can deliver the output up to 2 kilohertz, but you can also select the output data rate out of that. In this mode, you can enable an optional sync out square waveform to synchronize your system with exactly the samples time. But you can also do it the other way. If you want to synchronize, for instance, your GPS receiver, your GNSS receiver on the IMU, you can have access to a 1 PPS signal, for instance, and then you can put this PPS signal on the clock input, and we will scale automatically the clock input to generate internally the 2 kilohertz. That can be perfectly aligned on the top of a second, for instance. You can also input your own 2 kilohertz input to completely bypass the internal clock. So many possibilities to interface the pulse on your system. A brief introduction of the manufacturing. This is, we developed a 100% automated calibration process on our 2-axis rotary tables. So Emric will talk much more about that, but this is really an important aspect on the Pulse-40 and all the other systems that we deliver at SBG Systems. We deliver with each sensor a calibration and a validation report, which guarantees the performance level of the IMU. And also this fully automated process minimizes any quality issues since we limit all the human interventions to the minimum level. The risk of mistakes is really low. We have a screening process that makes it possible to take away any sensor that is not fully compliant with the specs. This slide will conclude my presentation. So back to you, Alan.
Thank you, Alexis. All right, members of the audience, you've heard about the Pulse-40, its particulars, excuse me. Now we're going to look at the applications, and for that we'll turn to Shaun McGuigan. Shaun is responsible for business development in the aerospace and defense markets at SBG Systems. He holds a PhD in nuclear magnetism from the University of Kent at Canterbury in England. Shaun has extensive experience in the development of micro electromechanical systems and ring laser gyroscope-based inertial systems with L3 Communications and Honeywell, as well as the development and integration of SASM GPS receivers. More recently, he worked as a consultant for companies such as Sensinor, Crossbow Technologies, iXblue, and PolyExplore. He joined the business development team at SBG Systems in July of last year. Shaun, we're all anxious to hear about applications. Please proceed.
Hey, good morning, Alan, and thank you for that glowing introduction. I really appreciate it. Yeah, so today we're going to talk about this exciting new product from SBG Systems, the Pulse-40 IMU. This product, as I like to say, is designed so that your system design doesn't flatline and actually has a good pulse. And what we're going to talk about in this section primarily today are some of the things that maybe are related to the first poll question. We're going to talk about markets, competitive advantages, why this is a tactical grade IMU, and then what the key benefits and features are of this brand new product from SBG Systems. So just to frame what it is we're talking about here in just one chart, this is the Pulse-40. It's a miniature MEMS-based IMU, the first one of its kind from SBG Systems, and we're very excited that this product is coming to market this month, and we have a lot of optimism that this product will be widely adopted for a wide range of applications, as highlighted in the first poll question. So on the left-hand side, we have some of the key benefits of the Pulse-40 IMU, sort of more of the, some quantitative, some qualitative. It's one thing that's particularly, I think, going to be valuable, particularly to this international audience that we have here today, is the fact that this is an ITAR-free product. So don't have to worry about that when you place an order with SBG Systems in France. Obviously, there are some export restrictions on the 2,000 degree per second variant of this product, but it's nothing like ITAR, believe me. This product also comes, unusually, especially when compared with the next best alternatives, it comes with a 2-year warranty, and that's straight out of the box. You don't have to pay extra money for an extra year, as a lot of people do these days request you to do. So please keep that in mind when you're looking at this product versus others. It's MIL Standard 810G qualified, which is extremely good for a product of this nature. And you will find, once you contact our sales organization, hopefully immediately after this webinar, that this is an extremely cost-effective product as well. There's some great technical features, as highlighted on the right-hand side. It's 0.8 degrees per hour, which makes it tactical grade, some 1 degree an hour. Very good performance from the gyro drift standpoint. It's very low weight, 20 grams. You hardly even know you got it in your system. 11 cubic centimeter volume, again, minimal, and only 0.3 watt continuous power draw. So obviously, this is great for people who want to do deep integration. You can put, as Alexis said earlier on in his presentation, you can put this IMU directly on your circuit card assembly, integrate it with your GNSS receiver, your signal processing software, and you've got an entire integrated system in a very low volume for a very low power. Okay, changing gears just slightly here. We're going to look here at the MEMS inertial market expansion that's taken place over the last decade or so, and also sort of show you where SBG Systems plays in the overall navigation industry, and then more specifically with respect to MEMS. So this plot here, it's a little busy, my apologies. On the left, what I've tried to highlight here is requirements for IMUs, and there's again a qualitative. It's sort of from value added, such as consumer products, up to what you might call critical to human life, such as spaceflight, human spaceflight. And obviously the requirements are different, very different, depending on what the application space is. And that's plotted against and along the bottom performance. And you might think of something like in-run gyro bias stability as being a performance number that would typically differentiate between these different types of grades of product. Again, from the lower left personal nav section up to the upper right, which is strategic grade. You're looking at very big ring laser gyros, very large fiber optic gyros, things like that in that particular segment. Where SBG plays primarily is in the oval, the kind of the canted oval in the middle of the chart. We cover most of the center of the marketplace there, and it's right now is probably one of the largest, fastest growing regions of the entire marketplace, and we certainly think it's a great place to be. And that the new Pulse-40 IMU kind of fits slap bang in the middle of this market expansion area. There are some markets here that it's not necessarily specifically designed to address immediately. That may be changed in the future depending on what the demands are on this product. But most of the areas that you see on this chart are going to be covered by this particular product. And as you can see, performance is creeping up beyond tactical grade and starting to encroach on applications such as low Earth orbit satellites, military ground vehicle navigation, and things like that have typically been the domain of other sensor technologies in the past. Okay, so the target markets for the Pulse-40 IMU, and we can talk about this more if we get more questions on it, hopefully, highlighted on the right-hand side of this chart, and we've got marine, aerospace, and industrial. This product is suitable for certain defense applications. It was not specifically designed for defense applications in that there are certain things that certain defense applications require, such as 20-year storage life or salt and spray protection, have not been addressed with this initial release. That doesn't mean they won't be as we go forward, but this product would have to be integrated, deeply integrated into a system to make it suitable for those kinds of end uses. We are primarily right now focusing on things like platform stabilization, navigation, bathymetry, shown in the second column. As some of you may already know, we already provide heave sensors for platforms that retrieve rockets from famous launch companies, which we're very proud of. We're also looking at getting more into the aerospace market. That's not a market that we have historically been very strong in, but we intend with this product to push deeper into the aerospace market. I think this product's great for things such as satellite communication, pointing and stabilizing of sensor and gimbal platforms. Those kinds of aerospace uses, I think, are going to become much more prevalent for this product. And then finally on the right, industrial applications, robotics, autonomous vehicles, 3D mapping systems. This product is perfect for any of those particular areas. So we're going to do the application space here. What we try to divide it out into is areas where we feel this product fits most specifically. And I'm delighted to see that we put GNSS aided navigation first here, and that was the poll question that brought in the biggest number of responses. So looks like we got it right on that one, thank goodness. Autonomous vehicles, UAVs, UGVs, eVTOLs, these are all the kinds of applications that we are looking at for this product when integrated with your choice of GNSS receiver or GPS receiver alone. Pointing and stabilizing, again, as we move to the right, another great application area for this product. One of the great things about this particular IMU is that it is so small and so light that you can mount it directly onto your gimbal or onto your pan and tilt head right next to your sensor, whether it's a LiDAR or an EO sensor. And you don't have to worry about doing some kind of strap-down system with an IMU way back in the bowels of your hardware. It can be right on the motion head itself. And then finally on the right-hand side, an area that we are very deeply involved in right now, and that's post-processing applications. As I think a lot of you hopefully know, we also offer inertia post-processing software, which gives you centimeter level accuracy on post-processed data where you, for example, don't have good access to RTK data, or the RTK data was not good. And this product fits perfectly in with that product line as well. It allows you to put together your navigation system, collect your position data, and marry it up with your LiDAR imagery or your EOS sensor data or your bathymetry, and then transport all that data seamlessly over to our Q-inertia mapping software and be able to see exactly how good your mapping accuracy is, for example, and review what you need to do either with that data in the future, or how to actually make decisions based on the data that you've actually collected. Okay, this is where I thought I was. So at this point, I'm going to hand it back over to Alan, and he will do the experts part one.
Thank you, Shaun. We're going to open up the broadcast, the webinar, to some questions from the audience. And the first one comes in for you, Shaun. Some exact, excuse me, some curiosity about exact figures for precision, size, performance, bias, stability, and maturity level.
Yeah, these are all extremely good questions. This product is, okay. This product is basically, it's a tactical grade IMU, as we mentioned earlier on, 0.8 degrees per hour bias instability, very low angle random walk, very comparable to what is required for many navigation applications. And it comes in an extremely small swap, 20 grams, 11 cubic centimeters, and less than 3 watts. I mean, those are industry-leading numbers. They're not the kind of numbers that you're going to find everywhere on the marketplace today at all. This product is perfect for integration. It's designed to be mounted directly onto a circuit card assembly or printed circuit board, and we also provide a starter kit, which makes it super easy to get up to speed on this product. It's a USB interface. You plug it into your laptop, and you start talking to the device immediately. And if you have any problems, we have people online, and we have actually a web page, and we have direct support online for people who may have any issues. So it's very mature. It's in production. You can buy it today. You can hopefully place an order right after this webinar, and hopefully that answers the question.
All right, thank you. Have a fairly long and detailed question for you, Alexis. I'll just read it out, and then you can take it. One audience member says, I'm glad that you noted how Allen variance is very limited and that vibration rectification calibration is also needed. It seems that 99% of analysts, even including experts, are oblivious to all that. Is SBG open to providing extensive calibration coefficients in compliance to a header record for a new IMU standard? Do you agree that Allen variance parameters found under stationary lab conditions are inapplicable under high dynamics? That's a mouthful, but or perhaps several, but I'll turn it over to you, Alexis, to answer that.
Yeah, thank you for the question. So yeah, I think that's an interesting comment, reminding that the lacks of Allen variance analysis. Of course, the Allen variance is only measured in a lab environment at stationary temperature, for instance. So it doesn't really reflect how the system will behave. How the system will behave in real conditions, like if you have a thermal variation, if you have vibrations, if you have dynamics. So of course this is only a limited way of analyzing the sensor performance. I still believe that it's an important aspect. We need to have a look at that, at Allen variance. But yeah, there are much limitations on that. Regarding making a new standard, so I am not really sure if I understood exactly the question. Maybe I think this could be addressed offline. We could probably have an offline discussion. But thank you anyway for the comment.
All right, thank you, Alexis. And I want to emphasize to the audience that we do have people reviewing the questions, so even if I'm not able to get to them on the air, you will get an answer from the experts at SBG Systems. Shaun, another question for you. How does the Pulse-40 compare in costs and limitations to other IMUs on the market?
Yeah, it's a good question. The main difference between the Pulse-40 IMU and the next best alternatives, if you want to phrase it that way, are that basically the Pulse-40 IMU is an OEM product, and it's designed specifically for very high volume applications. We have in mind applications that would require over 10,000 units annually for this kind of product. It's not necessarily a product where you're just going to buy one or two and build a system and that's it. It's certainly a product that we think has very high applicability and very broad-ranging applicability. In conjunction with that, the Pulse-40 was developed, as I said earlier, it's developed for deep systems integration. What I meant by that was that you can use, for example, pick and place techniques to put the Pulse-40 on your boards as part of your automatic assembly line. All of those things are going to reduce not just the initial cost of purchasing the product, but the costs associated with integrating, developing, testing, and manufacturing. So all of these things have been considered in the development and design of the Pulse-40, and it sets it apart from other people's tactical grades IMUs, quite frankly. The other thing is that the Pulse-40 it's deployed as an integral part of your hardware system, and it's not an external appendage. It's not another box on the end of a cable or power supply or interface. It's actually deeply embedded in your system. It gains all of the protections of your system housing and hardware design, and reduces your overall system volume and cost considerably. So I think it has a lot of advantages in the tactical grade marketplace that aren't addressed by other products right now, and we're very optimistic that people will recognize those advantages quickly and integrate this into their systems design.
Thank you. We're going to keep you busy, Shaun, by turning right back to you in the second half of your presentation. But first, we will have a poll question for the audience. Lori, go ahead, take it away.
Absolutely. Coming up on the screen is that second poll question. And the question is, what is the most important feature for your IMU? And although on the screen it does say select all that apply, we'd like to ask you on the honor system here to select your top 2 options. So top 2 we're looking for size, weight, and power, performance, qualification and reliability data, direct integration on PCB, or rugged design. So it looks like we're coming in with 54% size, weight, and power, 83% performance, 35% qualification reliability data, 9% direct integration on PCB, and 19% rugged design. So Alan, any thoughts here?
Well, other than that, not too many people are highly invested in direct integration. I'm going to turn to Shaun for commentary on this.
Yeah, thank you, Alan. I appreciate it. So this is not out of line, I don't think at all, with what we would have anticipated for a tactical grade IMU. Performance, I think, for this kind of product is always key in people's minds, and especially when you see that the #1 application that people are interested in is for navigation. For navigation during GPS outages, GNSS outages, the IMU has to deliver. It has to have good bias performance. It has to have good noise performance, and it has to be extremely stable. So no surprises on performance as being the #1 category. And I think we deliver there. I think if you look at the numbers, the Pulse-40 IMU delivers in that category, and I'm not concerned at all. I think we have a great offering. #2, size, weight, and power. Again, I'm not surprised. People don't want large, unwieldy boxes that consume huge amounts of power, huge amounts of volume, and add weight to their system. A lot of the systems that people are fielding like these days, such as very lightweight UAVs, can't handle those kinds of requirements. They need something that they can fly, and so having low swap is perfect, and the Pulse-40 IMU meets those needs head on. So I'm happy to see that as well. I think the direct integration on PCB, just to comment on that, people haven't had that available to them in the past. And so they've been used to having to deal with big boxes with lots of cables and power supplies and interfaces that they don't like. So it may take a while for people to get used to the fact that they've now got an option to put something directly on their circuit card assembly and integrate it deeply into their system. And that could be a new game changer for us.
Thank you, Shaun. I see the questions coming in. We will have another longer question and answer period concluding the webinar after the second half of Shaun's presentation and one from Emery. But for now, let's go back to applications, part 2, Shaun.
Thank you, Alan. Okay, so we're going to touch here in this section, short section, on some of the things that we talked about in terms of uses of the product at the beginning. And we're just going to highlight a couple. We're not going to go through every single one exhaustively. We'll just pick a couple and explain why we think this IMU is well suited for these specific applications. First one we're going to start with is pointing and stabilization. Maybe I should have started with nav, but that's the way the slides are. And what we've got here on this chart basically is we've got a table on the left where we put down some of the key requirements for each application. There's a list. It's not exhaustive. It's sort of the probably top 4 or 5 that people normally look for, and then why the Pulse-40 delivers in terms of its performance numbers and how these key into how you use this product in a specific application. So the Pulse-40 IMU has a lot of great characteristics for this particular set of applications. It's very high bandwidth. You need a high bandwidth in order to be able to be responsive to the motion of the platform. 480 hertz is a very, very, very respectable number for this kind of an IMU, and allows you to use it in systems with very high dynamics. The data rate, again, equally 2 kilohertz. This is a very high data rate output serial data stream, and that's what we have heard people are looking for these days. They want high rate data. They want to be able to parse it themselves and decide how to analyze and utilize that data. They don't want people doing their own processing and averaging, and so that's why we provide it in this format. The device has extremely low latency. 2 milliseconds is extremely good for both the accel and gyro channels. This means that obviously the system is keeping up with the motions that it's sensing and provides you with timely information on how to close the loop on your system and maintain stability or whatever it is that's key to you in this particular world. The noise is low. Got to have low noise, obviously. If you don't have low noise, then your antenna or your EO sensor is going to be bouncing around uncontrollably, and that's not a good idea. So 0.08 degrees per root hour is an extremely good number, and feeds right into pointing and stabilizing applications. And finally, temperature range. Everyone needs systems that operate over a wide temperature range these days. A lot of these systems are used in a wide variety of environmental conditions outside, different parts of the world. They see different solar loadings at different times of the day, different diurnal cycles. So having full calibration is a must, and we provide -40 to +85 degrees C. From an nav standpoint, we think this is an ideal product for navigation and mapping applications, and we have a lot of experience in both of these areas ourselves. Again, the chart has the same format as the prior chart. Key requirements on the left, what the Pulse-40 IMU delivers on the right-hand side of the table, and then why this is important. Scale factor error on the Pulse-40 IMU is 1,500 ppm. I want to make it clear that this is not just a sort of a one-day scale factor measurement. This is what you're going to see over the lifetime of the product. This is derived directly from our Halt testing, and is you're not going to see anything worse than this over 12 months of continuous operation. We guarantee that it will be 1,500 ppm. It won't be 1,000 ppm on day 1 and 6,000 ppm on day 10. The gyro has very good bias instability. This is your minima of the Allen's variance curve, 0.8 degrees per hour. And as Alexi mentioned earlier on, this gyro stays below 1 degree an hour for a long, 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 long time. And that's probably even more important than the actual value that you see here, is the fact that it's consistent over an extended period of time. Large changes in this with time are not good for navigation systems. They just don't like it. XLVRW is, again, extremely low. It's expressed here, obviously, in terms of the number of G's in noise that you'd experience as a function of frequency, but it's very quiet. These accelerometers are extremely quiet, and that matches in with what you need from navigation also. Bit coverage on this product is excellent. We provide you with both startup and continuous bit, and the continuous bit is 100%, and that's for the sensor cluster and the processing involved with the data. So, and we can provide further details on exactly what that covers if people have an interest in knowing. And again, we use the MEL standard 810G as our benchmark against which to do a qualification on this product, which is basically what most people anticipate that they would be delivered in a tactical grade IMU these days, although it's not always available for a OEM style IMU. If you look at the advantages of this over alternate technologies, alternate ways of putting together IMUs, obviously the biggest advantages I think that we offer right now are related to packaging. What you're getting from the Pulse-40 is you're getting a full 6 degree of freedom IMU that's smaller than a single axis fiber optic gyro, ring laser gyro, or spinning mass gyro. So from a packaging standpoint, this is the product to pick. And you're going to get very similar to performance to low-end fog and other forms of gyroscopes that are in the marketplace today, but in a package that just is unmatched. The product not only is unmatched in terms of size, weight, and power, but it's also extremely resilient to shock. MEMS inherently is more resilient to shock than both ring laser gyros and fiber optic gyros. Any of you that have ever used either of those two products in environments that have high shock or high vibration, you know that they can have issues with mechanical failure. That's typically mechanical failure between for example, the fiber or the light source or the detector, which renders the device completely inoperable. You're not going to get this with this kind of MEMS device. If you get any kind of failure at all, it's going to be a gradual degradation. It will not be instant lights out. The other thing that's very amazing with these devices is the MTBF, the mean time between failure for the Pulse-40 IMU is being offered at 50,000 hours. And so if you compare that to other devices, this is an extremely high number. There are other devices on the market, ring laser gyro devices, for example, where the MTBF is only 2,000 hours. So be careful when you decide which product you decide to pick for your system, that it's going to last for your system design lifetime goals. And finally, ease of integration and use. This product is designed to be usable straight out of the box. You don't have to be an IMU expert. You don't have to be an inertial systems expert. You can have this product as a standalone item or as a starter kit. On the starter kit, it comes with a USB cable. You can plug it directly into your computer. It's on its own breakout board, and you can start collecting data immediately, which is, I think, is a big benefit for this product over other systems where you got to figure out, okay, what kind of drivers do I need? How am I going to hook it up? What kind of power do I need? Don't worry about any of that. It will work immediately. We also have a SBG Systems, very proud of this. We have a great dedicated online support resource system. I think probably they have the best support system that I've seen of any inertial products company, frankly. The website is outstanding. Everything you need to know about the product is available on the website. How you log the data, how you capture data, how you make changes to the IMU, it's all explained in detail. There's a quick start guide, there's a user manual, and we have real people, real life people that you can call and talk to, and they will walk you through how to use this product. So very user-friendly, designed to get you up and running in the shortest amount of time possible. Okay, back to you, Alan, for the next section.
Thank you, Shaun. We're going to take an in-depth technical look at the Pulse-40, calibration, qualification, and a number of other factors. And this is going to be courtesy of Aymeric Lemercier, a tests and qualification engineer at SBG Systems. He has a master's degree in science in general engineering with a specialization in hydrography and oceanography from ENSTA Bretagne. In the inertial field since 2017, he is in charge of MEMS sensor tests and IMU calibration at SBG Systems. Aymeric, let's take that in-depth look.
Thank you, Alan. I will talk about the technical overview of the Pulse-40. So to do that, first we will talk about the manufacturing process. Then we will proceed by the IMU qualification and specification, and we will conclude by the sensor cluster. When we talk about overall process flow of the Pulse-40, we need to understand that SBG system is manufacturing the project, then is doing the calibration, the storage, and we finish by the validation. This section won't talk about the manufacturing process, but we will go deeply in the calibration step, the storage, and the validation step, and the validation. SBG system developed its own software to do the calibration. So I put here an example of the interface. So it's SBG prod acquisition. So you can select the operator, the type of IMU you want to calibrate, and then select the application you want to do. There are several applications like flash the QR code, acquire the calibration data, then compute the model, acquire the validation data, and finish the acceptance test. If we want to talk a bit about the first flash QR code and identify device, you can see here the Pulse. There is a QR code, and you can flash it, and it flashes inside the device the name of the IMU, and you can have full traceability with the connected ERP system. Then, when we have this product, we want to calibrate it. So SBG developed its own calibration interface. So you can put up to 36 Pulse-40 in one calibration. The calibration lasts 13 hours. And this calibration interface is just put in the 2-axis red table climatic chamber to do the calibration. When we talk about calibration, we want to compensate the sensor errors from the accelerometers and the gyroscopes. To do that, we use the red table to simulate rotation, position, and thermal environment. The main idea is to compare the sensor output to the stimulus from the table. Here I put the equation. On the left part, we have the sensor ideal output, and we have also the sensor real output from the accelerometer or the gyroscope. And the idea will be to find the compensation to make the sensor really quite fit to the sensor ideal output. Here I put one of errors. The first part is the scale factor error. So the green curve represents the table, the table movement, and the blue curve represents the sensor output. The idea here is just to apply a coefficient, the scale factor, to make it fit the green curve and the blue curve. The second error is the bias, is BS, and we can see that there is an offset, so we need to apply an offset to correct this error. The third part is the non-linearity. This error is quite difficult to compensate, and SBG do it with taking a function of the sensor real output. And then at the fourth part is the WS is the noise that the sensor really had directly. At the end of the calibration, we need to find the sensor model to do the compensation for the bias, the scale factor, and the triad element. And with this compensation, we can compute the calibration report, which showed the residual error. Here I put two examples, one for the gyroscope and one for the accelerometer. They both have sweep. So we have the thermal variation from -40 degrees C to 80 degrees C, and we can see the bias error in micro G or in degree per hour for the project, the residual, and we have the requirement and we have the statute to know if this test was good or not, and also the global statistics on the data. We can add that also we look at the thermal hysteresis of the calibration, which is quite important for our project. Then after the calibration, we do storage. It can go from 1 week to a month. The idea is to know if the sensor model is really stable, and with that part, we can see if there is any drift in the model. After the storage, we can go to the independent validation. It consists in 6 hours test with 3 independent points on power from -10 degrees, 20 degrees C, and 60 degrees C. I put here the report, and the 3 first part term are for the bias. Then we have the noise, the scale factor, and the non-linearity, and we finish by the triad parameters. We have the requirement then and the status, and so we have a global status on the test. And when we finish this, we finish the final acceptance test, and the validation report can be the first part of the final acceptance test. Then we will need to do the second part of the acceptance test. The last part of the acceptance test is done at ambient temperature, and it's a functional test. We want to know the power consumption, the signal sent out, the status, and also how the gyroscope and the accelerometer are compliant with our requirement. And then when this is full pass with the statute, we can upload the customer firmware, and we will generate a fully automated PDF report, which will be uploaded to the SBG cloud. This concludes the production, and now we have a status of the project at the first time, and now we want to know what are the IMU real specification and qualification. So we need to do tests over temperature, vibration, electromagnetic environment, and time. This part is quite hard and needs a lot of equipment and data analysis. To do the data analysis, SBG Systems also developed a tool that will be able to take the data from the calibration and validation and do the analysis of all the data of the IMU in time or temperature. This is really interesting to see any drift in the manufacturing process. So here I put an extract of the SBG prod test. So you can select the date. Here is from the 10th of November 2021 to the 2nd of February 2022. The extraction is from validation, accelerometer. We are looking for the scale factor, all axis, and all temperature. So this generates a result of 162 data. And then we can have the statistic, and we can also plot the distribution of the data. So here we can see quickly a Gaussian on the data distribution of the scale factor on the 162 accelerometer. Then we did the data analysis on the calibration, but we need a full qualification plan to pursue the test. So we have several tests like the startup at high and low temperature. Here I put the figure of this test. So the equipment is on at 20 degrees C, then we go to the max temperature, the equipment is switched off. We just wait 1 hour, then we just start the acquisition. After 1 hour, we just go then to the low temperature. We just switch off the equipment, and then we just switch on the equipment after 1 hour, and then we can see the variation and if the system is compliant with startup high and low temperature. We do also vibration under random and sinus. We will talk about this later. We look also the bias after shock on the accelerometer and the gyroscope, the stability or noise. We also do check on the CBIT analysis. We'll talk about this a bit more later. And we also look at test and qualification for electromagnetic compliance. But this is not enough to qualify our IMU. We need also to do tests for like accelerated aging to estimate how the IMU, what will be the performance of the IMU after 1 year. So this is done with hot storage 10 days from 10 days at 85 degrees C, cold storage 3 days at minus 50 degrees C, temperature cycling, logistic vibration and shock, power on off 100 cycle, and power on 50 hours. At every step, we are evaluating the performance of the IMU to know what are the drift in the performance. Now, if I want to talk a bit about stability, we also do tests with Allen variance, like said Alexis, to look at the performance of our IMU. Here, I put the calibration plates. 13 IMU were in this plate, and we were ambient temperature and acquisition were done for 12 hours. So here is the raw data, and then we compute the Allen variances, and you can see that here we don't have this drift which is occurring on the gyroscope on the gyroscope. Now, if you want to talk a bit more about vibration, we do sinus and random vibration. The main idea is to measure the accelerometer bandwidth, vibration rectification error, frequency resonance, and behavior under and after shock. Here I put the Pulse-40 on a shaker. The first curve shows the performance of IMU and the random vibration on frequency 20 Hz to 2000 Hz, and from random vibration 1 GRMS to 10 GRMS. Here you can see the bias shift, which is known as the vibration rectification error. And then you can compute the vibration rectification correction. Here I put another test, here on a sine sweep on the shaker from 20 Hz to 2000 Hz. And with 5G peak, and you can see that at the beginning we can see the movement and then the movement disappear. With this decreasing, we can just evaluate the bandwidth of the accelerometer. Now we talk about qualification, but SBG system is also known to use cluster technology, and the Pulse-40 really benefits from this. So we will talk a bit like what is a sensor, the advantage of using a sensor, and what are the challenges and issues to overcome. The idea behind cluster is the fact that the main sensors are really tiny, and you can really take it into account in your architecture. And so the main idea between the cluster is to reduce noise. It's known that when you use a cluster, you can expect 1 over square root of n decreasing in white noise. But we can improve other parameters: thermal stability, the linearity, the vibration behavior, and the reliability. Here I put an example of a bias stability of a gyroscope. the green curve represents 1 gyroscope bias stability. The red curve represents 6 virtual gyro bias stability. And at 1 time second, you can see that we're really decreasing the white noise for 1 over square root of 6. And you can also see that the bias stability is increased with the cluster. But as we put several clusters in our system, there are challenges to face. We can't sampling a lot of MEMS sensors, so we need to define what are the targeted performances. We need also to know how we can synchronize all the sensors. Then we will have also to adapt the calibration tool and know also what we will be doing with good and bad sensors. Here I put the SBG cluster. So how we do to implement the cluster in the Pulse-40. During the calibration, all the sensors in the cluster are monitored. And then we apply complex and finely tuned weighting factor criteria to compute the virtual gyroscope or virtual accelerometer. And we also do advanced CB. The weights are evaluated regarding several parameters like noise, thermal specification, and also the MEMS global behavior. The first figure at the top here represents the sensor ID. We have here 6 sensors with 3 axes, and we can see the distribution of the weight factor regarding the noise, the thermal, or the MEMS behavior. So which is quite a good example of how we implemented after the calibration the weighting factor. And to conclude, I will talk about the continuous bin test implemented in the Pulse-40, which can be really important for demanding application. So here we have the acceleration. We can see that some shocks are applied on the Pulse-40. Some status are raising. We have the accelerometer in range that is really common. But we also have the y-axis that are rising, which are showing that the cluster shows differences between the data. So this is quite relevant to the fact that we can just check on how the cluster is really behaving, what the behavior of the cluster, and if the data are reliable. To conclude, I will say that SBG Systems has an industrial process for Pulse IMU production. So we can see that we use 2-axis rate table. There is a storage then to see if the sensor model is really fitted to the IMU. We add validation, independent validation, and we have a fully automated report display on the cloud. SBG Systems also do tests to qualify the IMU performance from the calibration data analysis, environmental test, or functional test. And we also guarantee long-term life of long stability of our project. And the sensor cluster technology is also a good aspect of our Pulse-40. And this made us able to improve accuracy and stability with also a CB with 100% coverage test. So this is how we guarantee that we deliver IMU that meets the specification. It's finished. Back to you, Alan.
Thank you, Emeric. We'll turn to questions in a little bit. Meantime, we have some means for you to contact SBG Systems. You see them there, North America, EMEA, and Singapore. And there's also an option to find your local partner online. And we have some resources for you. The SBG Systems website, which is, Shaun mentioned, is quite extensive, quite helpful, quite in-depth. There's a leaflet on the Pulse-40 IMU itself, and a web page also supplying more information on the product. We have an extensive set of questions here. First question for our SBG experts: what are the impacts of the IMU packaging on the initial MEMS gyro performances, the bias and angle random walk and so forth, the other characteristics that you have cited?
I will take this one. That's a very, very interesting question. Actually, this is a key parameter to get a good IMU. You need to make sure that your packaging is not affecting the performance. It is clear that the MEMS sensors, the MEMS element can be quite sensitive to mechanical stress, for instance. So when exposed to a mechanical stress, the MEMS sensor, the MEMS chip by itself may be affected on the sensor bias. Typically, the bias will be an important aspect, but all the sensor characteristics can be affected. So this is why on the Pulse-40 we integrated a robust aluminum design that makes sure that all the sensors are rigidly installed and will not be affected by any constraint done by the integration, by the user integration. We also check that all the sensors are correctly installed within the IMU during our calibration and validation process. You can check with every single IMU we deliver. There is an associated validation report that specifies all the performance characteristics of the sensor to confirm the specs.
Thank you. A question for you, Aymeric. During the calibration, is there any compensation of the IMU cross-axis?
Yes, indeed. During the calibration and during the full thermal cycle of calibration, we are measuring the cross-axis, and so we can do the compensation to make sure that we have no problem of alignment, of misalignment at the end of the calibration, so we are fully compliant with the cross-axis compensation with a polynomial.
And a question for you, Alexis. How do you compare with other miniature MEMS IMUs on the market?
So technically speaking, there are some other good IMUs. We will compare mostly with the tactical grade IMUs modules, and what will be a really, really different aspect on our product is really the very, very specific calibration and validation process that has been designed for a very, very high performance products, and that we deliver also on miniature IMUs such as the Pulse-40 with an individual validation report for every single unit we deliver. So that will be probably a key differentiation, the association of high performance sensors with cutting edge calibration procedure.
All right, I'm going to pause the Q&A for a moment. I got so excited by some of these questions that I rushed right into it without giving the audience a chance to answer a question. Let's have our final poll, Lori.
Let's do it. Okay, coming up on the screen is that poll, and we'd like to hear from each of you. Which performance parameter is the most important for your IMU? In this one, we're going to ask that you select one response: noise, bandwidth, bias stability, thermal stability, scale factor, linearity. All right. Looks like 16% noise, 16% bandwidth, 54% bias stability, 8% thermal stability, 5% scale factor, linearity. So any thoughts here, Alan?
Well, I'm going to defer to Alexis for this one.
Yes, we can see that, of course, the bias stability is the major parameter that is analyzed by most of the IMU users. As I mentioned at the beginning of this presentation, this is a key factor for sure, but obviously it is not covering all the aspects of an IMU performance. Noise and bandwidth are also well represented. I think it's important when we consider thermal stability, which is not that well represented, such as also scale factor or linearity. It's important to remind that the bias stability parameter is only applicable at a purely constant temperature. So at some point, everyone needs some certain level of thermal stability, and I think that's a very important factor to mention. Some IMUs that can be, for instance, soldered directly on a PCB will have some difficulties to maintain these characteristics, for instance, because of the soldering process that might affect the calibration. So it's for us it's a quite important factor to make sure that the IMU will behave in all the conditions, and of course the bias stability remains an important factor for us as well.
Emeric, a question for you. Is the Pulse-40 able to measure the Earth rotation?
Actually, the Pulse-40 is have quite good capacities when we look at capabilities when we look at the noise and everything. So indeed, we can think that it's able to measure Earth rotation, but as we have problem at the startup bias, we cannot really have a fully measure of the Earth rotation if we don't know the bias at the startup. But during the calibration, we take into account the Earth rotation to do the compensation.
Thank you. And Alexis, is a question about the internal sampling frequency. Is it limited to 2 kilohertz?
Yeah, that's a good question. The internal main loop, which is running all the calibration algorithms, and the output generation is running at 2 kilohertz. That's for sure. But it's important to remind that we have the internal accelerometers and gyroscopes that are sampled at a higher frequency. So it's 4 kilohertz for accelerometers and 6.6 kilohertz for gyros. This oversampling allows to reduce the noise as much as possible, increase the resolution of the internal ADC, and it will also improve the performance in vibrating conditions.
And a question about aging. Do you apply an aging step on the sensors before calibration?
Yes, that's also an important aspect on the calibration process. So we have always a kind of accelerated aging to process that is performed before the calibration to stabilize the sensor characteristics before we apply the calibration.
Thank you. And a final question, just to wrap up, a fitting one to wrap up. Emeric, how are the calibration, validation, and specification criteria evaluated?
To do the evaluation and to do the requirement for calibration or validation, we are using the SBG Pro tool and statistic to evaluate the RMS and or the 3 sigma, the 1 sigma or the 3 sigma value. And this allows us to have a good representation of the performance of the IMU, as we have a lot of IMU tested on our facilities or our equipment.
Thank you. Well, we've wrapped up right on time, as it turns out, so good on everyone. I'm going to send the microphone around the virtual panel to give each of our speakers a chance to have a concluding comment. Let's hear from Alexis, then Shaun, and Émeric. Alexis?
Yeah, thank you everyone for attending this webinar. I think there was very interesting presentations and also very interesting questions from the audience. So I am really glad that we had this opportunity to discuss about all these technical aspects.
Shaun.
Sorry, thank you, Alan. Yeah, it was extremely good webinar. I enjoyed it tremendously, and hopefully the enthusiasm will continue to build as we roll this product out and it gets into the hands of the end users. So feel free, whoever's on the other end of the line, please feel free to reach out to our sales organization at SBG. Their contact information is provided. We're willing to provide you with whatever data you need on this product line, quotes, technical support, whatever it happens to be, and we look forward to hearing from everyone.
Émeric.
Yeah, thank you. It was really interesting to go deep inside our technical calibration, qualification, and the cluster. It was really challenging topic to address, and it was really interesting to present this today.
Thank you, gentlemen, for all your perspectives and for the information on this exciting new product. Thanks to SBG Systems for sponsoring the webinar. I'm Alan Cameron at Inside GNSS Magazine and Inside Unmanned Systems, where in the latter magazine you'll see a brief webinar recap. You will also receive a link to review, revisit, re-experience the webinar, and to share it with your colleagues, anyone else who may be interested. Thanks again, everyone, for attending, and have a wonderful day. Laurie?
Thank you, Alan. And again, thanks for joining us. This is Laurie Dearman saying, hope we see you on the next one. Bye for now.